name is Francesca Casadia. I'm with our institute in Chicago. I probably have a hard time keeping us to the time being Italian, but I'll try my best. The session that we're entering into is, I think, a very important one. And I think David Saunders, his phrases will continue to be cited over and over again here. We can certainly say that the portable XRF and XRF techniques have become really part of the basic toolkit that we all use, and it's very widespread. And I really look forward to the panel discussion about this, because there are certainly many opportunities, but also many issues. But it's definitely one of these instruments that we use to elucidate and engage with history and our cultural heritage. So we have a very rich session today. Our first speaker is Nick Barbi. He holds a BS degree in material science from Lehigh University and a PhD from Resnick Polytechnic Institute. He has founded or co-founded 3 manufacturing companies in the EDX field, and he holds a number of US patents on electron detectors. He is currently CEO of PulseTor LLC, a manufacturer of X-rays and electron detectors and electronics that recently joined and partnered with XG Lab in Milan, Italy, and some of you may have seen their instrument outside in the hall. He's going to present a talk on new portable X-ray spectrometer designed for XRF analysis and cultural heritage applications.
In theory.
And he's not here. Sorry, I didn't do very well on my search of a session chair checklist. Make sure your speakers are here. Tiana, you don't have any announcements? Oh, yes, actually, I have to announce this. It was searches later for later. But so we have this raffle, and we are going to actually have as prizes the new issue of Facture by the National Gallery of Art in DC that Barbara Berry and Merv Richards kindly gave to us for the raffle. And then we also have a number of the volumes on the handheld XRF book that has been mentioned many times today that Bruce Kaiser of Bruker has kindly given us for this particular raffle. And Nick is here.
I am.
So without further ado, Nick.
Thank you very much. Hello, everybody. This is a great slide. I have no information to show you on this slide, but it's just a fantastic slide to start with. I appreciate the opportunity to be here. My co-authors are Roberto Alberti, Tommaso Frizzi, and Mr. Celani from XG Lab in Milano, Italy. And I'm from PulseTor in Pennington, New Jersey. And we're very happy and proud to be an industrial sponsor of this symposium. And we thank everybody. Tierna and Chris and Susan have been a great help. And it's a pleasure to be here. And I promise I will not take up the whole time allotted to me. Just a little bit about who PulseTor is. We're a company that makes accessories for electron microscopes. We make SDD detectors, we make electron detectors, we make electronics. And because of our association with that business and being electronics manufacturers, we worked very closely with the people at Politecnico Milano. And that's how we met the group, which later became XG Lab. And we are now the distributor for their product in the US, and they distribute our product in Italy. This is one of our claims to fame here. We just introduced an X-ray detector for an electron microscope that has a built-in, an X-ray detector, an SDD detector that has a built-in electron detector. These, if you can see these 2 little chips here, are actual backscatter detectors. So the X-ray detector can The electron detector shows you the image that the X-ray detector sees. So this is essentially a low-angle backscatter electron detector, but right from the line of sight of the X-ray detector. So you see all the absorption, you see the topography, everything that the X-ray detector itself would see. So we call this the SDD with vision. And this is really how we got working very closely with XG Lab. We make digital pulse processors. They are optimized for SDDs, which are a little different than the SILI detectors were. And they can operate at very high rates, but the problem with, or the difficulty with electron microscopy X-ray analysis is that you have the low energies to deal with. So our pulse processor is specifically designed to do a very good high rate analysis of spectra with low energy components. We have 5 worldwide patents on the device. And this, you see there's an analyzed count rate or an output count rate of 185,000 counts per second in this spectrum with only 37% dead time. Pretty impressive spectrum. The resolution at manganese, 136 EV, despite this very rapid count rate. So that's a little bit about PulseTor. XG Lab really started in this business as Politecnico di Milano, and some of the people there for many, many years have worked on analysis of art objects. This was one of the original detector systems that they utilized. So this is the forerunner of ELIO. You see here some analyses that were done. This was a question as to whether this was originally La Lupa or Il Lupo. And some analysis was done in a sensitive area here to determine if the bronze composition was the same as the rest or added later as it was suspected by some. It appears that it was always La Lupa. Here's another statue, and you can see the idea of the instrument that we have out in the foyer. You can see how it evolved from this kind of work done many years ago. Fresco painting, I'll just quickly go through that. This is ELIO, and if you've walked by, many of you have walked by very fast, but we've been standing out there for 2 days. You see this instrument, and at the end we'll still be there, so you can take a look at it. But the analysis head is about 2 kilograms, and in it is the X-ray tube, 50 kilovolts, adjustable in 1 kV steps from 10 to 50. Typically, we use a rhodium target tube, but you can buy others, but I think the rhodium is pretty generally acceptable. It has a spot size of about 1.5 millimeters on the sample. The collimator at the tube is about 1 millimeter, and because you get some divergence, it spreads to maybe 1.5 millimeters. Possibly you get some information from as much as 2 millimeters, but typically about 1.5 millimeters is the spot size. We have a built-in camera that takes a photograph of the area that you're analyzing. A pretty high-quality photograph, and you can adjust the illumination so that you can get a decent image, except perhaps on very highly reflective metal surfaces, it might be difficult to do that. We also have 2 laser beams built inside, so the one laser beam is axial, and one is oblique, and as you position let's see, just go to here. As you position the fine Y control of the device as it's going towards the object, assuming painting on the wall, this would be the horizontal motion. You see that the laser beams coincide, and you get 2 beams on the sample until you get the position right, and then they coincide to 1. If you get too far away, they separate again. So that's one of the ways that we get very good reproducibility in the analysis. We have two vernier positions, two X and Y slides that allow you to do fine positioning. I found initially that, we just had the one Y position for the convergence of the laser beams, but it was clear that rather than move the whole tripod, another transverse fine control was useful. So out there we have two. Very simple change to the system, but a lot of utility. So you can do very fine XY positioning. And with the tripod post, you can also do the Z positioning right here. And this is, it can be a fairly fine positioning as well. One of the things I've learned when I was visiting the Walters Museum a couple of weeks ago is that when you lock down the Z position, you do get some movement of the head. So we've learned that just tighten it up a little bit to create some tension, and then you can get very good XYZ control. And of course, you can move the whole tripod. The tripod's on wheels, or can be on wheels if you like, and we have it set up that way out in the foyer. You have a ball joint grip here so that you can articulate the head any which way. You can have it pointed down, pointed horizontally at any angle. And the tripod itself, we chose one that's fairly lightweight but sturdy. And it doesn't matter, you can pick one that's a little bit lighter, or you can pick one that's heavier duty, but this is the one that seems to be a good fit for the instrument and for the weight. And you see the head is also cantilevered off the center axis, so you need to have a fairly sturdy tripod. I think, one thing I didn't mention here, instead of plug and play, we plug and analyze. We didn't think play was appropriate. We have all the setup for helium flush. Since it is a non-contact instrument, there is a space between the analyzed object and the tube and the detector. And the instrument comes equipped with a valve for running helium through it. And you can flush helium through that point to get better light element analysis. Typically, the instrument is pretty good, especially with high levels of light elements and detecting the light elements without the helium flush, but of course, helium flush would be better. And since it's non-contact, you don't have the opportunity of creating a vacuum. And the idea has been all along with the design of this instrument that non-contact was the goal. You also see the dimensions, but it's easier just to go out and look at the instrument in the foyer. It can be put inside an enclosure, of course. You can have XYZ control inside the enclosure. You can do many things with it. But then it's not a portable instrument anymore. But certainly the head comes off the tripod with a quick release, so you just snap it off and lift the head off and put it back on again. So that head can be used in a variety of different ways. Not handheld, because again, you have that open end with X-rays potentially coming out of it, so there's not that contact shutter that you might have learned to expect. So, but you can mount it on a table, you can mount it in some sort of fixture, or inside the enclosure like we showed in this slide. The analysis software is quite sophisticated, more akin to a laboratory type instrument than a portable instrument. It uses a PC, it's always hooked up to a PC, so you have a full suite of analysis software. And this just shows that the flow where you start with a spectrum, you do peak identification. They called it in their version of this slide the automatic element guess. And I took the word guess off, but that's really a good description of it. You do the background fitting, subtract the background, the peak fitting, and finally the concentration analysis by fundamental parameters. So it does do a nice job within the limits of what you would expect with fundamental parameters with an error-based system. That is, you don't have the light elements really to do a good analysis job on, and you have to normalize the concentrations. That's the one standard you have with standardless analysis, is the total of the concentrations. So you assume that all the concentrations equal 100%, or you can do stoichiometry and assume there's certain types of oxides and come up with an oxide percent. This is what you see in this particular case. It is, here's the concentrations, and I can't quite read them, but gold, silver, and copper. Here's the image that you get. This, you'll see there are two other image positions that you can select or not. One of them is using the built-in camera on the laptop so that you can take a picture of the operator. That's sometimes good, sometimes not good. People were worried that the instrument always came with my picture next to the analysis object, but that's not the case. And we went to the FBI and did a demonstration there, and they were very upset to find that their picture had been taken along with their badge information. And that was, they had us immediately wipe that information off the computer. So you can choose to have that picture or not. And then there's yet another camera that could be put in here, and that's just a webcam. So you can mount it on a little tripod somewhere, place it on a table, Velcro it someplace, and it takes a picture of the overall setup. So you can see the object, the analysis head. You can get an idea of the overall setup of the experiment. So here are the, you see a linear and log to scale, a log display. You get the raw spectrum, do the peak identification, in this case the gold lines, copper, do the background fit, peak fitting, and then the spectral analysis. In this case, they were just showing off, I think. They did the analysis in 0.3 of a second, which is which one would never do, but it shows that the analysis results can be quite good in very short analysis times if the sample permits, like in this case, a nice metal sample. And the analysis results are down here, are quite close. This is a 17% silver, 7% copper, and 76% gold. And if you can read those, they're fairly close to those analyzed concentrations. So because the instrument is very stable, the electronics are very stable, and I'll talk about that in a minute, the reproducibility is quite high. You can get very good statistics with this tool. Also, there's a place for filters. You can see that on the instrument. They're manually set. We have 4 filters and a blank where you can put any filter you would like. And that fits right in this little opening in the instrument. You can see the effect of having different filters. This is our standard filter set, but as I said, any filters can be chosen really, or you can make your own. And you see the effect is to reduce the background from the tube. Here's a spectrum of a NIST glass with barium at 450 ppm. And you see this out here, antimony about the same, and cadmium, which is here. And you can see that with and without the filter. So in this case, you can dramatically see the improvement that the filter allows. So the normal strategy in doing the analysis is that you do a 50 kV analysis. I like to run the current up pretty high. It's a 4-watt tube. I didn't mention that. So with 50 kV of accelerating voltage, you have 80 microamps of current at your fingertips. So I like to just maybe start with 50 kV and 60 microamps and then see where to go from there, whether we should use a filter or not, change the conditions. These are just more different filters. One of the points I'd like to make about XG Lab is their kind of amazing development of some electronics. As I said, I worked with them back when these electronics were being developed. And Carlo Fiorini, Antonio Longoni are very famous people in the SDD world of R&D and development, and they are the people behind XG Lab. This slide just shows that the silicon drift detector resolution just can't get much better than it is now. It's just, you know, no matter what you do, it isn't going to get much better than this. You're going to have to go to a different semiconductor material, a different technology altogether. So the change and the improvements are all in the electronic side. They developed this preamplifier called the Cube, which because it's a millimeter cube device that if some of you, I know one of the previous speakers, Jessica, said she loved microanalysis, as I do, so I'm glad there's at least two of us here. But the standard had always been a device called the JFET, and the JFET, you might know it from Oxford. It was called the pentafet. The pentafet was a patented device from Oxford, and it became the standard worldwide, and being the first amplification stage of the sensor, where you convert the current pulse from the sensor to a voltage pulse, so you can then amplify it. And for as long as I've been in the business, which goes back to the early 70s, the FETs, the JFETs, were always used. And about maybe 4 years ago, 5 years ago, Carlo Fiorini at Politecnico Milano decided that he could make a better CMOS FET with different technology, put more of the amplification devices up close to the sensor, and make a better overall device suitable for SDDs. And they did that very successfully. Here's an example of the JFET and the Cube on the same detector. Not the same physical detector, but the same detector specifications. And as you can see, there's peaking time here. Maybe the next slide actually is more useful. Yeah. So as you decrease the peaking time or shaping time of the amplifier, you get more and more count rate throughput. So that, as I mentioned, the performance of the detector becomes limited by the electronics now, because the silicon detector is just about peaked out with respect to its resolution capability. And as you see, because the Cube optimizes at these very low shaping times, where if you want a certain throughput, say 100,000 counts per second throughput, you need to set the peaking time somewhere around 1 or 2 microseconds. And when you do that, the JFET really deteriorates the spectrum. And so this is an amazing development. Luca Bombelli was one of the graduate students at that time, now works for XG Lab, did the simulations for this device. Nobody thought it would work, and it just works in a fantastic way. So this will be the way everybody now all the EDX companies will eventually use this, this Cube technology. Here's an example at high rates. The blue spectrum is with the Cube, and you can just look in here and see the smearing of these peaks with the JFET technology, and it's pretty impressive. You look down here, you can't even tell what's going on with the JFET, and here with the escape peaks and so forth. So it's quite a dramatic improvement. Nothing to do with the detector. It's all in the electronics. Here's some examples of some work that was done. And you see how the LEO is up against but not touching the artwork. And you see some different analysis points of the and the spectra. This is actually a very nice way to display spectra, by the way. I think looking at spectra sometimes is overrated. And looking at these bar graphs showing the relative compositions is a very nice way to do this. So from the sky point of view, we saw white lead, ochre, and cinnabar. You can see the mercury here. You can see the iron, no manganese. And then this, this cloak area, you see the elevated iron and manganese associated with it. You also see very high arsenic. So the conclusion was that this was an umbra, which was indicated by the high iron and manganese, and possible use of arsenic-containing pigment like orpimento or realgar, and indicated by high, and then I run out, but the high arsenic is the... Okay, I'm going to go through these fairly quickly, and I want to just show that the use of the camera in the system. In this particular gold leaf analysis, which was, you know, in these, in this object that you see here, there was quite a bit of difference between the gold and iron ratios in the different gold leaf sections that were analyzed. And they thought that was quite interesting. Maybe there was a different period. But in fact, when they looked at the images, you can see that the erosion of the gold leaf was much heavier in this one section with the low gold. And so whether or not the compositions were different was overshadowed by the fact that the degree of erosion was quite different. And so this could be seen after the fact. You might not even notice it while you're doing the analysis, but because you keep a record of the image with the spectrum, you can go back and look to see if this was, if there was anything unusual with respect to the area analyzed. These are some images provided by the people at MoLab, part of the Charisma organization, and we thank Professor Brunetti for allowing us to show these pictures. But one of the things it shows is there's 2 or 3 pictures here which just show the flexibility you have in orienting the head to meet the analysis requirements. So here it's facing straight down, and you have a flat piece. You can put papers or photographs on some sort of even a styrofoam material with a cutout in it, so you don't have a hard surface to scatter back X-rays and get a spectrum from underneath. It's a very flexible kind of system this way. This was also from the Charisma group, and in this case there was an analysis of a codex, and I'll just read what I wrote here. This was the light element analysis issue, looking at the aluminum, which you can see is at 50 kV is non-recognizable. But by adjusting the voltage, in this case, the blue is at 50 kV, the pink is at 20, and I don't know, this looks the same to me, but anyway, 20 kV, and you can see the fact that you can get a very nice aluminum peak from this spectrum. This is done in air. This was not done in helium. And also on this green area, it was shown that the green areas have been painted by mixing a yellow pigment or pimento, which was determined by the very high arsenic content, with a blue pigment, and the suspicion that it's ultramarine is not confirmed, but you could see that the green was made by mixing the yellow with the blue pigment. Here's another painting that just will go to this, where we've looked at several different yellow and orange regions, and you can see here that they're all identified: cadmium sulfide, lead chromate, mixture of lead, chromium, and antimony, and so forth. So you can see all these quite different yellow and orange pigments. And then really, finally, I'd like to show this. And Austin Nevin, who's been very helpful with us in this presentation and organizing this for us. We thank him and also all the people that are listed on this slide. But the final issue was what yellow pigment was in this artwork. And the XRF system shows that there is the presence of chromium, and the conclusion was it was yellow chrome pigment. But all of you know far more about this than I do, and we've seen some great presentations here about some nice work that's been done by the authors here and their colleagues. So I will just end this, and again, thank you very much for the opportunity. I will end with another great picture. So I think this is just a great field to work in. I've been in this field only a relatively short time. We started representing XG Lab around August of last summer. And so it's been a very much of a crash course for me in this, but a great group to be associated with. So thank you very much.
Thank you very much, Nick. I know that there is a lot of interest for this new instrument in the field. Are there any questions from the audience? Aniko? Microphone is coming. It's the conservation science toolkit to the rescue.
Thanks so much for introducing this instrument to us. And I was just curious, are the detector and source collimators just sort of open, and then out there's no
That's correct.
No film in front, right?
We have a cover for them, and the cover can either be removed or they're totally exposed, or you can put the cover on and there's just a little opening, and that actually becomes a point where you could use the instrument as a contact instrument. And then everything's covered. If this were metal samples, for example, there'd be no problem in putting this soft rubber cover right up against the metal sample. But yes, and you're welcome to come out and take a look when we're through with the session here.
Okay, thank you very much.
Any other question here from Scott?
So it's always hooked up to your PC, right?
Yes.
Okay, is the bandwidth... Hello. Is the bandwidth that's needed small enough that you could use a Wi-Fi to be on the ground while somebody's up high, putting it in position for you and so forth?
Yeah, good point, John. It is, in fact, an improvement that's coming in the system. Being tethered to the cable isn't always the best approach. So yeah, the Wi-Fi would be a nice solution to that problem.
Can take a few more questions. Annika again.
Okay. Oh, there's one more.
Sorry, I had another one about the electronics. In many of the EDS systems that use these electronics, you're able to choose the processing speed so that you could kind of gain faster data at the expense of resolution. Is that adjustable in your
question.
system?
It's almost like I paid you to ask this question. But with our electronics and with the cube and SDDs, you can really set them at one time constant. Whether it's, we tend to use peaking time, which is a little different than shaping time, but say 1 microsecond peaking time, and you just leave it alone, because it doesn't change. If you go up to very high rates or low rates, the resolution stays the same. So the key is to use a short enough peaking time that you can get all the rates you ever want to have, and then you just leave it fixed. Okay. But to answer your question truthfully, there is a selection inside this system, because when they first introduced it, they didn't always offer their cube. At that time, it wasn't yet a full-fledged product, so they had different type of JFET preamplifier, so they allowed that selection. But at this point, it's not a useful, and it'd be the same with an EDX system on an SEM. You would just set it at one value and just leave it there.
Yeah, it's very impressive
Yeah.
resolution.
Any more questions? No, Annika will not take money, but an instrument if you think that. Let's thank Nick.